In this video, we're going to be taking a look at finding extrema. And extrema are just another name for maximums and minimums. So the first type of extrema that we're going to be looking at is something called an absolute or a global extrema. So if we have f that is a function defined on some interval I and it contains some point c, then we know that f of c is called the absolute minimum of our function on that interval when f evaluated at c is less than or equal to all values of our function anywhere else on this interval. So that's basically what this is saying, is if you can find a point where you evaluate your function at that value, if its value is less than all other values of y on that interval, then that point represents the absolute minimum. And then similarly, the absolute maximum is found if the value that we evaluate f at is greater than or equal to all values of y on that interval. So if f of c is the absolute, or f of c is the absolute maximum of f on that interval when f of c is greater than or equal to all values of f of x in that interval. Okay, so basically what this is saying is an absolute minimum is the lowest that our graph ever, will ever reach, and the absolute maximum is the highest that our graph will ever reach in terms of y value. Okay. So in this first example, we want to find the absolute maximum and or minimum values if they exist on some given interval. And it's the same function, it's y equals x squared for all of these, but we're looking at a different interval. So here we have a domain of all real numbers. Here we're on the closed interval from 0 to 2. Here's a half open interval and then an open interval. So what I want you guys to do is try this problem, right? So you're trying to find the absolute maximum, so the highest that your graph ever goes, and the absolute minimum, the lowest it ever goes, if it exists on these intervals. So go ahead and sketch the graph on each of these intervals, and then try and find any of your absolute maximums and or minimums on those intervals. So go ahead and pause the video now and give that a shot. All right, so I've gone through and graphed all of our functions on the intervals. So when the function is going from negative infinity to infinity, it's the entire graph, and we know that it's just our y equals x squared parabola here. When it's going from 0 to 2 with the brackets, remember the brackets mean that we have a closed interval, so the endpoint will be included. Those points are closed. A parenthesis means that it's an open interval, so that point would be open. So we have an open and a closed point there, and then here we have open points because they are both parentheses. So how does that impact our absolute maximum and minimum values? So first, let's go ahead and try and find the absolute maximum in part A. So absolute maximum. So the absolute maximum, like I said, is just the highest that my graph ever reaches. And because this graph, it's not shown to do that, but because this graph is growing upwards forever, right? It goes up forever. It is growing infinitely large, so there's never a maximum value that it reaches. So there's actually no absolute maximum. Now, as far as the absolute minimum, what is the lowest that this graph ever reaches? So the lowest that my graph ever goes is here at a y value of 0. So the absolute minimum, when it talks about the value, so in this case it's asking about what is the value. The value is just the y coordinate, right? It's the y coordinate. So the absolute minimum value is 0. It occurs at the point 0, 0. So if you're talking about the absolute minimum, it occurs at an x coordinate of 0. Its value is 0. So that would be the value there. So the absolute minimum would be 0. In part B, what is the absolute max? So the absolute maximum here, the highest that my graph ever goes, so it stops here at x equals 4, sorry, at y equals 4, when x is 2. And because this point is closed, that means it's included in that domain. So its absolute max is 4, and again, it occurs at the point 2, 4. Sorry, there we go. So we would just take the y value there. The absolute minimum in this is, again, 0. Again, it happens at 0, 0. In part C, Again, because the point is closed, we have the same absolute maximum of 4, again occurring at the point 24. But in this part here, we have this open circle here, right? That open circle. Now that open circle is indicating that that point is not included. So we're getting as close to a y value of 0 as possible, but we can never actually quite reach it. So if we said that our absolute minimum was something like 0.1, well, then we could ask ourselves, well, can I get any closer to 0? Well, yeah, I could get 0.01. Well, can I get any closer than that? Well, yeah, 0.001. And we can get as close to 0 as we want without ever actually reaching it, right? So its limit that we're approaching is 0, essentially. But we can't actually reach that point of 0. So there is actually no absolute minimum here. Now, in part D, because the highest potential point that we would reach and the lowest potential point that we would reach are both open circles, they're not included in our domain of the curve here, we can say that this has no absolute maximum or minimum. So this has no absolute max or min. Okay. So one of the theorems that we are going to be looking at, it's a pretty important theorem. It is called the Extreme Value Theorem. Now, there are, just like with most of our, like with continuity or any of our other theorems, there are conditions that need to be satisfied in order for us to be able to show that this holds true. And some of the conditions that we need to consider when we're looking at the Extreme Value Theorem are as follows. So first, f needs to be continuous on some closed interval from a to b. So if f is continuous on a closed interval, so it means that on the endpoints it's defined, right? So it also, that's another important piece, right? So that it's a closed interval. So the endpoints are defined. So if it's continuous and it's closed, then f has both a minimum and a maximum value. And when we're talking about minimum and maximum values, we're talking about absolute. So we're talking about absolute minimums and absolute maximums on that interval. So an absolute minimum and or maximum, actually both an absolute minimum and maximum are guaranteed to exist if we have a continuous function that's defined over some closed interval. And they can happen kind of in 3 different ways, right? So if you have a curve like this, it's monotonic, right? It's decreasing over the entire interval from a to b. Then you would get a maximum and a minimum at the endpoints. So you'd have a maximum point here, right? The maximum value at A, and your minimum value would occur at B. If you have something like this is kind of like a sine curve or something. You could have a situation like this, right? Like a sine curve where you have maximums that occur on the interior, right? Inside your interval, and a minimum that occurs in the interior. So your maximum would be here at x sub 2, and your minimum would be this value here at x sub 1. So your maximum value would be m, and your minimum would be little m there. And you could also potentially get a maximum or a minimum, right? If this graph was flipped, you'd have a maximum, but where one of them is in the interior and then one of them's at your endpoint. So we see that we have this maximum here at my right endpoint, and then my minimum is actually somewhere on the interior of this interval from a to b, right? So it's like here at x sub 1. Now, if this graph was flipped like this, maybe, right, like this, you could see we'd have like a maximum here in the interior, and then our minimum would be here at that endpoint. And it could do the same thing like this as well, where you have your maximum here and your minimum here. So it's possible to have maxima and minima in the one in the interior and one in the one at the endpoint. They could both be in the interior, or they could both be at the endpoints. Okay, so, and that's talking, the extreme value theorem, again, like I said, is talking about absolute maxima and minima. So if we're trying to find relative or local extrema, so local maximums, local minimums, what are we looking for? Well, first of all, what is a local extrema? So if we have some function f, it's going to have a relative minimum, or sometimes called a local minimum, at some point c if our function is less than or equal to f is the value of f at c is less than or equal to f of x for all x in some open interval. So in this case, we're talking about an open interval that contains c, which means c has to be in the interior of some interval. So there needs to be values to the left and right of c in order for this to work. So essentially this is telling us, since it has to be surrounded by some open interval, that a relative maxima or a relative minima cannot occur at an endpoint. And this idea is kind of up for debate. There are some books that define endpoints as having the ability to be local extrema. It really kind of varies from book to book, teacher to teacher. So if you move forward and your professor or your teacher says, no, endpoints can be a relative or local extrema, then you just kind of follow whatever your teacher is saying. Now, as far as the AP test is concerned, the AP test is not going to have you look for local or relative extrema at endpoints because of this discrepancy. Okay, so we're not really too concerned about trying to find relative maxima and minima at the endpoints of a function. We're only going to be looking at those in the interior. And so a local maximum occurs if the value of our function at that point is greater than all values kind of immediately surrounding it, right? So again, on some open interval. Now, this little open interval basically just means that we're looking at values immediately kind of surrounding it, right? So immediately surrounding. And is it higher or lower than all of those points on that interval? And that will determine whether we have a maximum or a minimum there. So here at C, right, we can look at kind of some open interval or immediately surrounding it. We can see at C that this point here is the highest point of that little area. Now, is it the highest point overall in our function? No. So that means that it is going to be a local maximum, Here at E, so is E the lowest point? It's not the lowest point, but it is the lowest point in some immediate interval surrounding it. So this is going to be a local minimum. Here at A. Now, A is lower than all of the points kind of immediately surrounding it that are defined, but because it's not defined over here on the left-hand side, this actually is not going to be a local minimum. This is not going to be a local minimum. However, this point is the lowest point on our entire curve from A to B. And because it's the lowest point on our curve, this actually represents our absolute minimum, right? It's the lowest point overall on our entire curve. Okay, so what about at D? So we can see here at D, our function's not differentiable at D. We have like a point here, but it doesn't say anything about differentiability when looking at relative extrema. So if it's the highest point or lowest point in some interval immediately surrounding it, then it is either a local or relative, some kind of extrema, right? So we can see that the point at D is the highest point in some immediate surrounding area, which means it's going to be a local maximum. But not only is it a local maximum, in this case, it's actually the highest point of our entire function. So it's actually an absolute and local maximum. And then here at B, remember at the endpoints, we are not talking about relative maxima. And so really we only would consider the maximum or minimum if it's the absolute highest or absolute lowest. And because it's not the lowest point or the highest point in this blue curve, this is not an extrema. So this has no extremum. So it's not an extrema there. It's just the end of our interval. Now, if we're actually looking for local extreme values, right? If we're looking for relative maxes and mins or local maxes and mins, they're the same thing, right? Then what has to be true? Okay, so if f has a local maximum or a local minimum at some value of x equals c, and if f prime of c exists, so there's a couple things, right? First, f has to have a local max or a local min at some value of c, And if the derivative of our function at that point exists, then we are guaranteed for the derivative to equal 0. Now, the converse of this is not always true. So just because the derivative is equal to 0 does not necessarily mean that we have a local maximum or a local minimum. However, if there is a local maximum or a local minimum and the derivative exists, then the derivative must be 0. Let's kind of go back to that other graph that we looked at in that previous previous definition. So if you look here, right, if we look at this, we can see that we have a local maximum here at C, and we have a local minimum here at E, right, and we have another local maximum at D. Now, at C, our curve is nice and smooth and continuous, so it is differentiable there. And you can see we have this horizontal tangent line drawn, which means that the slope of that tangent line is going to be 0. However, here at D, right, at x equals D, our curve is not smooth. It goes up to a point like this, and then it comes down like this. So we have this kind of corner, this cusp here. Which means at this point here at D, our function is not differentiable. So because it's not differentiable, we aren't sure about what the derivative is, right? So the derivative does not exist, right? The derivative does not exist here. Just because the derivative doesn't exist does not mean that we can't have a maximum or a minimum. So that's where we're saying like the converse doesn't necessarily hold, right? So just because this is not differentiable does not mean it can't be a maximum or a minimum. Does not mean it can't be a maximum or a minimum. Here though, right, it's smooth and continuous, and so we see again the horizontal tangent line is telling us that its slope is 0. The derivative at E is 0. Now, what are we looking for when we're trying to determine maximums and minimums? So to help us figure out where a maximum or a minimum could occur, our kind of looking at this, right? Our slope is either going to be 0 like this, or it's going to be undefined. So those points where our derivative is 0 or undefined, we call critical numbers. So a critical number of a function is a number c such that f prime of c is equal to 0, so the derivative is equal to 0, or f prime of c does not exist, or the derivative does not exist. So if you can find your derivative where it's 0 or where it does not exist, those would be potential places where we will have extremum. Now, just because we have a critical number doesn't mean that we're guaranteed to find a maximum or a minimum. These are just the potential places where a maximum or a minimum may occur. So let's go ahead and take a look at an example of finding critical numbers. So we want to find the critical numbers of f if f of x is equal to x to the 3/5 times 4 minus x. So remember, to find critical numbers, this means we want to figure out where f prime of x is equal to 0. Before we can do that, we need to take the derivative. So we have two functions here, so this tells me they're being multiplied. So this tells me I need to use the product rule. So f prime of x is equal to the first function, x to the 3/5, times the derivative of the second. The derivative of 4 minus x is going to be -1, plus the second function, 4 minus x, times the derivative of the first. So that's going to be 3/5, x to the 3/5 minus 1, which is going to be -2/5. And then we'll clean this up a little bit. We're going to get negative x to the 3/5 plus, this is going to be in my numerator and that's going to be in my denominator. So it's going to be 3 times 4 minus x all over 5 times x to the 2/5 power. Now, to figure out where this is equal to 0, ideally we want to get a common denominator and this to be a single fraction. So I'm going to need to multiply this term here by the denominator here. So we're going to multiply by a 5x to the 2/5 on top and bottom so that we can get this written in as a single fraction. Okay, so x to the 3/5 times x to the 2/5. When you multiply powers with the same base, you add the exponents. So that's going to be x to the first. So we're going to get negative 5x here. And then that's going to be plus, let's distribute this out. We're going to get 12 minus 3x. So plus 12 minus 3x, all divided by our common denominator of 5x to the 2/5 power. And remember, this is what f prime of x is equal to. We want to know where this is equal to 0 or where f prime does not exist, right? Does not exist. So it's undefined, or it does not exist when the denominator is 0, and it's equal to 0 when the numerator is 0. So let me kind of just simplify this a little bit first. Here we're going to have 12 minus 8x when you combine your like terms. Then we have 5x to the 2/5. Okay, so to figure out where our critical numbers are, we're going to set the numerator and denominator equal to 0 and solve. Set the numerator and denominator equal to 0 and solve. Okay, so 12 minus 8x equals 0 is going to give me that 12 is equal to 8x. Divide by 8, and we're going to get 12 over 8, which reduces to be 3 over 2. So x is equal to 3/2. And then setting the denominator equal to 0, 5x to the 2/5. This is going to give me when my function is undefined, but it's also going to represent a critical number. And if we divide by 5 and take the 5th, and raise to the 5 seconds power, right, that's going to be when x is equal to 0. So this is 0 when x is 0. So our two critical numbers, so critical numbers are x equals 0 and x equals 3/2. Those represent my potential places where I have extremum, right? Where I have absolute maximums or minimums. Or sorry, relative maximums or minimums. Now, one thing to note is if you're looking for a local max or a min, in order for it to actually be a maximum or a minimum, the function has to be defined at that value, right? Kind of like we saw in this here. We can't have a minimum or a maximum if our function is not defined there. So if in order for this to be true, the derivative must exist there, which means it has to be continuous and it has to be defined there. So our function has to be defined at the value in order for an extremum to exist. Okay. So even though 0 makes the denominator here undefined, I can effectively plug 0 into this, so it is a potential candidate for a maximum or a minimum. So we want to find the absolute maximum and minimum values. Now, the key to this problem is the word absolute, right? And remember, absolute means that we can happen at endpoints, right? So absolute extreme values can happen at endpoints. Local cannot. So when we're evaluating this, we want to know where is the derivative 0 or undefined, what's the value there, and then also we need to check the endpoints because we're looking at some closed interval here. Right, so basically this is telling us it's defined on the interval from -1/2 to 4. Okay. This curve here, I know it behaves nicely. It is a, right, this that curve there. It's just a cubic. It's polynomial, so it's continuous. It is differentiable everywhere. But because it's a polynomial, this tells me that by the extreme value theorem, because we're looking at some closed interval, we're guaranteed to have an absolute maximum and a minimum. Because it's a continuous function over this, actually everywhere, but over that interval. So to figure out where we have absolute maximum and minimum values, we need to first figure out where are the potential relative maximum and minimum values, because those could also be absolute. Relative maximum and minimum could be absolute maximum and minimum. And then we also have to consider the endpoints, because you could have one of those situations where you have something like this, where you have an absolute minimum at an endpoint, but you have an absolute maximum somewhere in the interior. And so that has to be considered as well. Okay. So what is the derivative? F prime of x is equal to, so using the power rule, we get 3x squared minus 6x. We want to know, first of all, this is never undefined, so we really just need to know where is this 0. So figure out where this is 0. We could factor, so factor out a 3x. We get 3x times x minus 2. Set each factor equal to 0. From this, we get 3x equals 0, and we get that x minus 2 equals 0, giving us that x is equal to 0 and x is equal to 2. So these are not the only 2 points that we have to test. We also have to test x equals -1/2 and x equals 4. These are the values of our endpoints, and they could potentially be some absolute maximum and minimum values. Now remember, when we're talking about the value, it's the value in our original function. So how do we figure out which of these represents our absolute maximum or minimum values? Well, you just plug these 4 numbers into your original function and look at which one's the highest or the lowest, which one's the biggest or smallest value. So we're going to evaluate at -1/2. We're going to evaluate at 0. We're going to evaluate at 2. And we're going to evaluate at 4. So you can go ahead and just plug all these numbers into your calculator. I'm not going to necessarily work all this out. So just plug these numbers into your calculator and see what you get. So if you go through and you plug all this in, f of -1/2 ends up being 0.125 in your calculator. That's 1/8. F of 0 gives you 1. F of 2 gives us -3. And f of 4 gives us a value of 17. So if you plug all those things into your calculator, these are the values that it's going to spit out. So which of these is the largest? Which of these is the largest number? Well, the largest value is this one here. That represents our absolute maximum. So this is our absolute maximum. So the absolute maximum value is 17. It occurs at 4, right? So it's at the point for 17, but the actual absolute maximum value is 17. Which of these is the smallest? The smallest number, remember, most negative, not small, closest to 0. So the most negative value here is here at 2, and that represents our absolute minimum. So the absolute minimum is going to happen at the point 2, -3. And again, the actual value of the minimum is -3, and the location here is at x equals 2. So we ended up with a maximum at the endpoint and then a minimum somewhere in the interior. So that's why it's important to check the endpoints in this as well, because it could lead to a maximum or a minimum. Okay, so in example 4, this is a graphing calculator question. So let's go ahead and just read this and get the setup, and then go jump to the calculator to work through this problem. So it says, use a graphing calculator to find any local or absolute maximum and minimum values of our function f of x equals x minus 2 sine x on the interval from 0 to 2 pi. So it's a closed interval. Again, because it's a closed interval, that tells us we can use the extreme value theorem. Because I know that f is going to be continuous, because I know the sine is continuous, and I know that x is continuous, so that composite is, so that difference is going to be continuous as well. So let's go ahead and jump into our calculator to take a look at how to solve this, this question. Okay, so here's our calculator. First of all, we need to be in radian mode, so make sure you click mode, or sorry, click on the mode, make sure your calculator's in radian mode, which it is, because we're dealing with sine here. So go into y equals, and let's go ahead and punch in our equation. So the equation was x minus 2 sine of x. Close your parentheses. And let's go ahead and take a look at this graph. Okay, so our graph looks like this, but this is graphed from like -10 to 10. And we actually don't really want that whole thing. We just want to look at our interval where we're defined. So let's go ahead and go into the window. The x-min, that's like the furthest left that we want to be. So let's make that 0 because we're going from 0 to 2 pi. Tab down into the max, and that's going to be 2 pi. So go ahead and type 2. And then pi is right here above the caret key. So second caret is going to be 2 pi. It doesn't really matter the scale that we go by because we're going to be using the calculator to calculate these things anyway. And the maxes and mins don't really matter because the whole graph was kind of self-contained in that. So let's go ahead and hit graph again to take a look at what we have here. So I can clearly see that there's like a minimum somewhere around here and a maximum somewhere around here. The endpoints in this case are not going to be absolute maximum or minimum values. So we don't need to worry about that there. So how do we calculate the point where this happens? So to do that, we're actually going to use a feature in the calculator in the second calculate. So it's going to be second trace to get into the calculate options. And we want to calculate, let's first do a minimum because that was the first one that showed up. So we're going to calculate a minimum. So you can hit, either tab down here or just hit 3. And we're going to calculate a minimum. So the left bound, that means you just have to take your cursor and put it somewhere to the left of where we think there's going to be a minimum. So cursor over, and let's say there, hit enter. So you can see this vertical line is kind of telling us this is the left bound of where the calculator is going to be looking. Choose somewhere to the right of it, hit enter. And then when it's asking you to guess, it's just saying like point to where you think it is, right? It doesn't really matter. You could just hit it over here anyway, and it'll figure it out. But kind of get close, hit enter, and it tells us the minimum. So our minimum value, right, is this y value here. So the minimum value is negative 0.685. Negative 0.685. So let's go ahead and take a look here. So the absolute, so the absolute minimum was negative 0.685. What was the x-coordinate? The x-coordinate where that happened was 1.047. Remember, for rounding, we want to keep 3 decimal places for the AP test. So that was at x equals 1.047. So this was at x equals 1.047. Oh, whoops, I closed that. Let me open this up again. I accidentally closed my calculator, so let's go ahead and open this again. Okay, so there's our minimum. And we're going to do the same thing to calculate the maximum, but we're going to go second trace into the calculate options and choose option 4 this time. So we're going to choose option 4 to calculate a maximum. So left bound, it just has to be somewhere to the left of this. It doesn't have to necessarily be close. Like I could have it, I could have it, sorry, I need to calculate this again. I could have it here if I wanted. Right bound, it just has to be somewhere to the right of it. So there is fine. And then guess, kind of try and get close. We think it's somewhere around there. Hit enter. And the maximum happens at x equals 5.236. But the y value, the actual value is 6.968. So let's go ahead and look at the absolute max. Right, the absolute max is what did I say it was? 6.968. 968. And that was at x equals 5.236. 5.236. This isn't really as important. It's asking for the value, so these are the important numbers there. So go ahead and sketch your curve on the axes, and then we used our calculator to calculate these.